All right, folks, we're now ready for section 3.10, the last section of chapter 3, polynomial and rational inequalities. So let's get behind the concepts here. First question here to consider is, where on a graph would f of x be greater than 0? So again, f of x is our function value. We can also consider it y greater than 0. So that's asking us, where is our y positive? If we were to consider our coordinate plane with the x-axis and the y-axis, we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. All of our y values are positive up here above the x-axis. Okay, so that means quadrant 1 and quadrant 2. Likewise, if they ask us where on a graph would our function value be less than 0, again, that's where our y values are negative. That would be down here below the x-axis in quadrant 3 and quadrant 4. So let's consider, where on a graph then could a function change from positive to negative and vice versa, from negative to positive? Let's take a look at the two graphs below to answer that question. So first, the polynomial here in graph A. If we're to look where our function is positive, all of our function values are positive values all the way in quadrant 1 and quadrant 2. The negative function values, as we talked about, are down here in quadrant 3 and quadrant 4. So where do they change signs? Here at our x-intercept and here at an x-intercept. We have an x-intercept here, so it doesn't mean that they have to change signs, but they could. Remember our intermediate value theorem. If we have two y values, one's positive and one's negative, then there has to be a 0 in between there because it's a continuous function. So one place where our graph can change from positive to negative y values is at the x-intercepts, or our zeros. Now let's take a look at this rational function. We still have all of our positive function values above the x-axis and all of our negative function values below the x-axis. But where do they change signs? Well, they also change signs here at 2, 0 at our x-intercept. But notice if we read the graph from left to right, it's going from negative y values here to positive y values here across our vertical asymptote. Now again, just because we have a vertical asymptote doesn't mean it will change signs on both sides. Over to the right, that vertical asymptote of x equals 4 is negative on the left and negative on the right. But it is possible to change signs at the vertical asymptotes. So that would be our second place. So just to recap, if we're dealing with a polynomial, we're only going to look at x-intercepts. That's the only place where it can change signs. If we're looking at a rational function, it could be an x-intercept. And remember, that's where our top of our fraction is equal to 0. Or it could change signs on either side of a vertical asymptote, and those are found where the bottom of our fraction equals 0. So depending on which function we have, we may look only at zeros or both the zeros and the vertical asymptotes. So let's try our first example where we're solving a polynomial inequality. And then they want us to graph it on a number line and express it in interval notation. Well, here are some steps. First of all, we want to set the inequality to 0, because remember, that's where things change when it crosses that x-axis. So if we subtract 3 from both sides, we get 2x squared plus 5x minus 3 is greater than or equal to 0. So this greater than or equal to 0 means we are looking for where the function values are positive and 0. Well, lucky for us, we've got a quadratic set to 0, so we can factor or use the quadratic formula. This one is factorable, so we will get 2x minus 1 times x plus 3 greater than or equal to 0. So the second thing we want to do is solve for x. We're going to ignore the inequality just for a second. Imagine we had an equals. This would give us a 0 at a positive 1/2 and at a negative 3. So in order to figure out where our function might be positive, 0, or negative, we're going to graph it on a number line. So graph these points on a number line. So we have a negative 3 and a 1/2. Does not have to be to scale. We're using this simply as a tool. And we know both of these values are 0. So both of these guys are going to be included in our solution. The problem is we don't know which of these 3 intervals is going to give us a positive function value. So I have the interval to the left of negative 3, between negative 3 and 1/2, and to the right of 1/2. So step 4, we are going to use test points in each interval to see which is positive. So what do we mean by those test points? To the left of negative 3, there are infinite number of negative numbers. I'm just going to choose one. I'm going to choose negative 10. I'm going to plug that negative 10 into my original equation, f of negative 10. And I can actually do that in the factored form, so that might help. I can plug in 2 times a negative 10 minus 1 times negative 10 plus 3. Well, I don't really care what the values are. I just care what sign it is. Negative 2 times 10 is negative 20 minus 1. So that's going to give me a negative number. Negative 10 plus 3 is going to give me another negative number. And negative times negative gives me a positive. So I know every function value to the left of negative 3 is going to be positive. Now we're going to do the same thing for a value between negative 3 and 1/2. If you get a chance to choose 0, I would. 0 is great. Love multiplying and adding zeros. So f of 0, this time we could plug it into the original before it's factored. We would get a 0 plus 0 minus 3. So that middle one would give us a negative. And then choose a value to the right of 1/2. It could be 1, it could be 10, it could be 100. We don't really care. But again, if I plug that in, f of 100, we don't care what the value is. We only care about its sign. So we could plug it into 2 times 100 squared plus 5 times a positive 100, and then minus 3. Well, we're pretty sure that's also going to be a positive number. So everybody to the right of 1/2 is going to be a positive y value. So since we are looking for function values that are positive and 0, then that means everybody here to the left of negative 3, including negative 3, works. And 1/2 and everybody to the right of 1/2 works. Those are our positive intervals. So that first left pink positive interval goes from negative infinity, using the parentheses, to -3 using brackets because the -3 satisfies the or equals to part union. We'll use bracket again for 1/2 since that gives us a 0. And then towards positive infinity, parentheses, for everyone else that gives us a positive y value. So set it equal to 0, solve for your x to find those points, graph the points on the number line, and test in however many intervals that gives you. Let's go to our second problem. Again, we want to set it equal to 0. So if we move the 7 minus 10x to the left-hand side and write it in descending powers, we would get 2x cubed minus 5x squared plus 10x minus 7 is less than 0. Now that I have it set to 0, this tells us I'm looking for where our function values are negative. We do not want where they equal 0, just where they're negative. Well, we have a polynomial, but it's not a quadratic, so we can't necessarily factor it right away, but we can use all of our previous knowledge, including the rational zero theorem, find factors of our last term, which would be plus and minus 1 and plus and minus 7. It's nice, they gave us a prime number. And factors of the first coefficient, which would be plus and minus 1, plus and minus 2. So our possible rational zeros would be plus or minus 1 over 1, which is 1, plus or minus 1 over 2, which is 1/2, plus or minus 7 over 1, which would be plus or minus 7, and plus or minus 7 over 2, which would be plus or minus 7/2 or 3.5. So we can't forget about the stuff we learned earlier. We may need to use it again later, out of the blue. So now we can plug in some of these values into our function to see which one of those might give us 0, and we can reduce it. I would start with something small, like maybe positive 1, since we already have some negatives in there. Let's try f of 1. We get 2 times 1 cubed minus 5 times 1 squared plus 10 times 1 minus 7. And that does in fact give us a 0. So we know that 1 is an x-intercept, a 0 of this polynomial. So let's divide by that 1 using our synthetic division and all of our coefficients from our original, 2, -5, 10, and -7. Bring down the 2, multiply by the 1. We have the 2 combine and we get a -3. Times that 1 is -3. Combine, 7 times 1 is 7. Bring up the 7, combine, and we get 0. And remember, we started with a cubic, x cubed, so we go down 1 degree, and we get 2x squared minus 3x plus 7 as our other factor. Well, we were hoping that this trinomial here would be factorable, but it's not. We multiply 2 times 7, we'd get 14, no factors of 14 that add to a -3. But we can use the quadratic formula. So remember, x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So when we plug this in, we get the opposite of -3, which is 3, plus or minus the square root of our -3 squared, which is 9, minus 4 times our 2 times our 7, all over 2 times our 2. Well, if we're to reduce inside that square root, we would end up with 3 plus or minus the square root of -47 divided by 4. This is not a real number. Therefore, those little 3 dots, not an x-intercept or 0. So we did all that work. We had to find out, but there's only one x-intercept, and that is x equals 1. So we can go to our number line. We're going to plug in 1. And remember, our 1 is where it equals 0, but we don't want where it equals 0 this time. We only want where it's negative. We don't have the or equals to bar. So the 1 will not be included, but it does split our graph into 2 intervals. Let's do a test point to the left. I would choose 0, love zeros, and a test point to the right, possibly 100. So if we plug in f of 0, we would end up with, in the original, a 0 minus a 0 plus a 0 minus 7. So the left side would be negative. And on the right-hand side, we have a positive 100. So the sign of f of 100 would be 2 times 100 cubed minus 5 times 100 squared plus 10 times 100 minus 7. Well, really, this first binomial there is really going to take over, and we're going to end up with a positive. So since we're only looking for values that would give us a y value that's negative, we are only looking for the left side, below -1. So our solution is from parentheses negative infinity to the left, all the way to 1 parentheses, since 1 is not included. When we are solving polynomial inequalities, we could also use our knowledge of end behavior and what the graphs look like. For example, in this top one, we know it's a quadratic. Our leading coefficient of 2 here is positive, so we know it opens up. So if we found 2 zeros, it has to be positive, negative, and positive. But trust me, there's a reason I showed you the number line. It's gonna be here in a minute. But you can always double check since you know what the graph should look like. Same thing for problem B. We have a cubic this time with a positive a, which means our function is going to go like this. And if there is only one x-intercept, we know it's going to go from negative to the left to positive to the right, which is what we got here in our number line. So that's a nice way to check. It's nice to know that number line method with the test points for our rational inequalities. We want to do the same thing. We want to solve them and then graph the solution set and express our answers in interval notation. Remember, there are 2 places where a rational can change signs. It can change signs at the x-intercepts, which is where this guy equals 0, as well as the vertical asymptotes, which is where this guy equals 0. So x-intercepts up here and vertical asymptotes down here. Luckily for us, our function is already set to 0. So since it's greater than or equal to 0, we are looking for values where our function value is positive or 0. So now we got to work with both. Let's find our x-intercepts first. So we'll take the top of x squared minus 4x plus 3. Let's set it equal to 0. It is factorable. We get x minus 3 times x minus 1. And if we solve for our x's, we get x equals a 3 and a 1. Since these came from the top, these will be included. So think of it as a colored in dot or a bracket. Well, to find our vertical asymptotes, we're going to set our denominator of x squared minus 4x minus 5 equal to 0. Luckily, this one is also factorable into x minus 5 times x plus 1. And on this one, we get x equals 5 and x equals -1. But remember, these are vertical asymptotes. These are values that are excluded from our domain. So these are not included in our answer ever. So they will have like the open circle or the parenthesis. So let's plot these 4 on our number line. Now be sure that you plot them in order. -1 is our smallest. +1 is our next. Then we have 3 and 5. And I recommend go ahead and make them colored in circles, like 3 and 1 are included because we have the or equals to. And then open circles at the -1 and the 5. Now, when we were finding the signs for these, I find it easier to use the factored form, which are top was x minus 3 over x minus 1, divided by the bottom, which was x minus 5 times x plus 1. And it's easier to look at each of those and see if you're multiplying a positive or negative to come up with the sign. So let's split up into our intervals. So this time we get 1, 2, 3, 4, 5 intervals. So let's focus on the very left interval to the left of -1. We can plug in a -10. So the function value of -10. Again, I'm just going to look at the factored form. If I plug -10 into the first binomial, that's going to give me a negative number. The next binomial, x minus 1, would give me a negative number. The bottom left binomial, x minus 5, would give me a negative. Next one would give me a negative, so that's a positive divided by a positive. So this left-hand interval will be all positive y values. If that confuses you, plug it in. Plug in -10, see if you get a positive or negative number. You can always put those into your calculator and use your table. You just need to show me on your exams and your quizzes how you found it or what you did to find it. Now let's choose a point between -1 and 1. Again, 0 is my favorite. So if we plug in f of 0, the top left, 0 minus 3 is a -3, so we have a negative. 0 minus 1 is a negative. Bottom left, 0 minus 5 is negative. But then 0 plus 1 is a positive. So on top, negative times a negative is a positive, but the bottom is a negative. Positive divided by a negative is a negative. Now let's plug in a number between 1 and 3. 2 looks pretty good. F of 2, again, we would have a negative times a positive this time over a negative times a positive. So this is a negative divided by a negative, which would give us a positive. Between 3 and 5, I would choose the number 4. So f of 4, that would give us a positive times a positive over a negative times a positive. So that's a positive divided by a negative. So you need to know your multiplication signs. And then the very last one, we can plug in 100 or 10, it doesn't matter. F of 10, they're all going to be positive. So we get a positive over positive, so that interval is positive. So let's color in the intervals that satisfy the original problem. Remember, the original problem was greater than or equal to 0. So we want to find out where our function value is positive or 0. Well, it's positive to the left of -1. It's positive between 1 and 3, but 1 and 3 gives us 0, so those are included. And it's positive to the right of 5. Our solution will have 3 intervals. The first left positive interval starts left to right from -infinity, and it stops at -1, but -1 is not included. Union. The next positive or 0 starts at 1, so we use bracket 1 all the way out to 3, bracket again, union. And then the next positive interval starts right after 5, so we're going to use parenthesis 5, since 5 is not included, out to infinity. And again, -1 and 5 are not included because those were values that made our denominator 0. Those are our vertical asymptotes. Now, our last example is going to have to use some algebra 1, algebra 2, where we're going to have to add and subtract rational expressions. So we still have to set this guy equal to 0. So that gives us 1 over x minus 4 minus the rational 3 over 2x plus 1 less than 0. Once we get it set equal to 0, that means we're looking where our function value are negative. The problem is we need one fraction on the left, one rational expression. So we have to add. That means we need to get common denominators. A little bit of scratch work here on the left. We have 1 over x minus 4. The other denominator is 2x plus 1. So we need to multiply the top and bottom of this first fraction by 2x plus 1 minus our second fraction of 3 over 2x plus 1. Well, now that 2x plus 1 is missing our other denominator, x minus 4. So we're going to multiply the top and bottom by x minus 4. Let's distribute the tops. We'll get 2x plus 1. And then we're distributing a minus 3. So that would give us a minus 3x plus 12. Those signs can be a little tricky. So that came from the fact that we had a negative 3 times an x minus 4. And remember, when you're adding fractions, you combine the tops, but you leave the denominators the same. We're going to go ahead and leave these factored, the x minus 4 and the 2x plus 1 in the denominator, since we're going to have to factor them eventually anyway. Let's combine like terms in the numerator. We get a negative x plus 13 over x minus 4 times 2x plus 1. And again, we can bring back down the less than 0. And now we are looking for our x-intercepts by setting the top equal to 0 and our vertical asymptotes by setting the bottom equal to 0. So our x-intercept is where the opposite of x plus 13 equals 0. We can add x to the other side, so we get 13 equals x. Now remember, in our original, it's less than 0, not or equals to. In this case, none of those points are going to be included. So we're going to have an open circle or parenthesis. Then to find our vertical asymptote, we are going to set our denominator, which is already factored, x minus 4 times 2x plus 1 equals 0. So that gives us an x value of 4 and a negative 1/2. Now these denominators are never included. So again, we're going to use an open circle and parenthesis. So let's plot these three on a number line. Again, be sure that they are in numerical order. The negative 1/2 comes first, then the 4, then the 13, giving us 3 intervals to look at. Oh, I lied, giving us 4 intervals to look at. Math teacher, I can't count. So a test value to the left of negative 1/2 could be a negative 10. So we can find f of negative 10. And again, I'm going to focus on the factored form, which was this guy here. The negative x plus 13 over x minus 4 times 2x plus 1 to determine our signs. And remember, this is the opposite of x up here. So if our x is negative 10, that's going to give us a positive 10 plus 13, which is a positive number, over negative 10 minus 4 is negative, times, that would be a negative 20 minus 1, that's negative. So that gives me a positive over positive. Then between negative 1/2 and 4, I would try the point 0. So f of 0, that would give us a positive on top. 0 minus 4 is a negative. And 0 plus 1 is a positive. So that would give us a positive over a negative, which is negative. Between 4 and 13, you could choose anything. I'm going to choose 10, f of 10. So the opposite of 10 plus 13 would still give me a positive in the top. 10 minus 4 is positive. 20 plus 1 is positive. So that gives us a positive over a positive. And to the right of 13, we can choose 100, f of 100. Remember, it's the opposite of x. So that's a negative 100 plus 13. So that's going to give us a negative number on top. 100 minus 4 is positive. 200 plus 1 is positive. So that's a negative over a positive, which will give us a negative number. So we want to know where it's negative. So that's between negative 1/2 and 4. And remember, none of these special values there are included. We don't have the or equals to. And our last interval of negative y values is to the right of 13. So we have two intervals that work. That's parentheses, negative 1/2 to 4, close your parentheses, union, parentheses, 13 to infinity, close your parentheses. All right, so that's it for chapter 3, polynomial and rational inequalities. So just quick recap, set it equal to 0, find your x-intercepts and or vertical asymptotes if you have them, and then check numbers in all of those intervals to see which intervals are positive and negative and satisfy the problem that you were given. All right, thanks for playing. Talk to you guys later. Bye.